Hello, everyone. Apologies for the delay there. I had a wee bairn who's still upset. Live episodes might still be delayed. I might need to do some hybrid half and halves for a little bit longer. Anyway, quick content warning because this episode will, of course, contain descriptions and images from a fatal train crash. So bear with me a second. There we go. Juggling. It's very hot. Everyone's juggling. It's yes. So sorry. On the 21st of October 2024, two Welsh regional services collided with each other on the line between Aberystwyth and Shrewsbury, resulting in the death of a passenger and serious injuries to three others. A week ago, the RAIB released their final report into this terrible crash. Then, only a couple of days later, two East Midlands services collided with each other near Bedford, killing driver Sean Burton and seriously injuring many more. We now know that the trigger for the collision was the rear train passing a red signal, but that only really opens up a lot of other questions which we won't get answers to for a long while. Therefore, we won't be speaking about it specifically tonight. However, by going through the RAIB report from Talerddig, not only can we understand what went wrong 2 years ago and understand what the industry must change to avoid this happening again, but we can also understand the mechanisms by which trains are able to collide with each other, how overlapping causal factors interact to break down safety redundancy, and how investigations like these proceed to give us the understanding to do better as an industry. Everyone, welcome to tonight's Rail Natter. So Talerddig, what is significant about Talerddig? It's had for quite a while after its construction in 1862 the deepest railway cutting constructed in the world. That's what Talerddig has. Other than that, not very much. It's kind of in the nowhere zone between kind of Machynlleth across to Newtown and Welshpool. There's a loop which is where passenger trains cross each other on their way, allowing the current service frequency to operate. For trains going from Aberystwyth across to Shrewsbury and Birmingham International. In terms of what happened, though, there's a lot for us to squeeze in, so forgive me if I press on at high speed. The RAIB have actually put together a very good video explaining what's happened. So before we get into the report itself, I figure the right thing to do is actually to go through that crash sequence using their video, but I will annotate over the top of it. So, at around 1926, on Monday the 21st of October 2024, two passenger trains collided near Talerddig, Powys. There it is. I'm replacing the audio for this because the audio was very gentle. Both train services were operated by Transport for Wales Rail Limited, TFWRL. I don't know why they didn't just say TFW, but that's fine. The trains were operating on Network Rail's Cambrian line. There's the cutting as it looks now. Notice the vegetation there. This is mainly a single track with passing loops provided at intervals to allow trains travelling in opposite directions to pass each other. You can see some nice fresh ballast there. There is the passing loop. Train 1 Juliet 25, the 1831 service from Shrewsbury to Aberystwyth, had been approaching the loop at Talerddig with the intention of stopping there. So this is what should have happened. This would then allow Train 1 Sierra 71, the 1909 Machynlleth to Shrewsbury service, to pass in the opposite direction. There we go. The Train 1 Juliet 25 would then have continued its journey towards Aberystwyth. The strange situation, the thing about this one is it's not a dynamic loop, so they... Anyway, right. However, it did not stop at the planned location and continued, leaving the passing loop onto the single line on which Train 1 Sierra 71 was approaching. There's the cutting. When the two trains collided head-on, Train 1 Juliet 25 was travelling at approximately 24 miles an hour, while Train 1 Sierra 71 was travelling at approximately 6 miles an hour in the opposite direction. Tragically, a passenger travelling on board Train 1 Juliet 25 lost their life because of the collision. 3 people on this train were seriously injured, including the train's guard, and 18 people received minor injuries. The driver of Train 1 Sierra 71 suffered serious injuries, and the remaining 5 people on that train all suffered minor injuries. Extensive damage was caused to both trains, although neither actually derailed. You can see the damage there to the cab. Damage was also caused to a set of points at Talerddig Loop. Essentially the points were run through. The railway line was closed until the 20th of October 2024, 7 days after the accident. So, also disruption associated with the incident as well. The accident was caused by train 1 Juliet 25 passing its authorised stopping position. There's the start of the loop. And entering the single line, which was occupied by approaching train 1 Sierra 71. So here's going through the loop. That's the stopping point where it should have stopped. Train 1 Juliet 25 passes authorised stopping position due to a combination of 3 factors. The wheel-to-rail adhesion was too low to support the braking levels demanded without sand being discharged, so trains have sanders to help with grip. It had been raining in the area, but the level of wheel-to-rail adhesion as train 1 Juliet 25 approached the loop was not exceptional for October. Train 1 Juliet 25 was fitted with systems which are designed to discharge sand into the wheel-to-rail interface and improve the adhesion. You can see the sand equipment, the pipe there taking sand into the wheel. During this investigation, RAIB found that the automatic sanding system on train 1 Juliet 25 did not operate before the collision. It looks pretty tired in this photo, doesn't it? Crikey. Probably due to electrical defects. Whoops. Yeah, the train was also fitted with a separate emergency sanding system which could be operated by the driver. However, this system was not activated. That's during the course of the accident, that is. Our investigation also found that the approach speed of train 1 Juliet 25 was such that the signalling system fitted on the Cambrian line, which is ERTMS ETCS, by the way, I think we're about to be told that, initiated a brake application which, in the absence of sanding, was greater than the prevailing wheel-to-rail adhesion could support. So it needs to be braking more gently, basically. The driver also made a similar brake application very shortly afterwards. This is what the inside of 158 looks like with the RTMS, by the way. Having passed this intended stopping point within Talerddig Loop, train 1 Juliet 25 then entered the single line beyond. So it's gone past it's about to go past the marker. There you can see the block marker. There were no engineered mitigations to prevent 1 Juliet 25 entering the occupied single line. So, set of trap points, for example. The area beyond the loop had exceptionally low wheel-to-rail adhesion and a steep downhill gradient. This meant that even though the brakes on train 1 Juliet 25 were fully applied, the train did not slow down as it ran towards 1 Sierra 71. So at this point, it's starting to go down. It's a very steep hill through the cutting. Meanwhile, 1 Sierra 71 continued in the direction of Talerddig towards train 1 Juliet 25. Because the driver of that train received no instruction to stop. This is because the signalling system could not automatically issue an instruction for the train to stop. So the ERTMS had no way to stop another train because of a breach of its own block. And the signaller had not reached a clear understanding with the driver of train 1 Juliet 25 regarding the position and movement of that train. And so there we go. That is essentially what... that's the sequence of events. Fairly well explained. I think that video is really good. It's on the RAIB YouTube as well if you want to read it and kind of watch it and get the original sort of narration as well. It's mildly less chaotic than mine is. So let's go through the causal analysis, shall we? And it's worth saying, episode 90 of Rail Matter, we've kind of gone through Leaves on the Line. It's worth a bit of a reread of that. There's a couple of other things I want to point out as well, which is... well, I'll tell you what. Let's first of all. So let's hold actually. So we're gonna flick through before we start talking about cause analysis. Let's kind of start flicking through let's start flicking through, shall we? So I'm also going to just go big face momentarily to make sure I've got this set up, which I do. Good. So here's the PDF. A reminder that I can flick through this quickly. If this is the sort of thing that bothers your eyes, do be prepared for that. So here's the document. Here's an RAIB report. For those of you who've not looked at RAIB reports before, it has a bit of a preface, and then it's got the contents page. It's got a summary which we can flick through. It's got an introduction which gives some of the key kind of context, things like units and which direction maps are and things of this nature. We've got the summary, so we've kind of gone through the summary. We don't need to go through that again. It's got lots of information there about how many passengers there were on each of the trains. You've got the track layout here. So again, you see in one direction there is a refuge. There are some trap points. You can see the way that trap points get used down at the bottom there. So you can see that trap points get used to protect running lines, but not from passenger trains. So generally, the reason we don't have trap points there is because in Britain, at least, the practice is it's generally that you would not use trap points to protect passenger lines from other passenger lines, because trap points are not a good way to treat passengers, frankly. So generally we use them in sidings where it's freight trains or light wagons or locomotives only, where it's railway staff are the only ones who might be submitted to that kind of event. So that's what we don't do. There are potentially physical things you could do, like you could have a long siding. You could extend the double track section kind of through the downhill, for example, but obviously Talerddig cutting is very narrow, so that'd be an extreme piece of civil engineering. You could run a short spur with a sand trap as one way of slowing a train. That is an option. Given there is a brief bit of level, that could potentially be a solution. But anyway, we might get some of that context later. Anyway, that's the track layout. So the train, the errant train was kind of in the up loop and ran through into the path of the train coming up the hill the other way. And you can see sort of the layout there. So you've got the speeds. These are in kilometres an hour because it's RTMS. So it's all in kilometres rather than miles an hour. So you can see there's the up loop, which is where the train was supposed to be parked but passed through. You can also see the fact that the loop sits on the level, and then as soon as you're beyond the loop, you're heading downhill, which is, as you can imagine, if you've got a situation where the wheels are sliding, that's not good. And so we've all kind of seen this. It goes through the Class 158, so there they are, talks about the two of them, the fact they're very similar, about the same age as I am. Those trains, I have a fondness for them. The signalling system, bit of context about the ERTMS signalling system. This was the major pilot kind of installed in 2011. Good grief, that shows how long ETCS rollout has been crunching onwards and onwards and onwards. Gareth pointing out there are trap points at Wrexham General on one of the live passenger lines, one of the few places where they exist. Yeah, absolutely. Not many out. I mean, there are a few out there, but not many. We generally don't do it. Another one, a set of catch points actually that we have on the Highland Main Line that I think we've talked about before, actually, on a very early episode of Rail Natter. So ERTMS is based on a suite of unified standards. Okay, so that's the information about ETCS going through there. So you can read that context. Discussion of the staff involved, including the signaller at Machynlleth. There is a signalling centre at Machynlleth that runs the system. Some external circumstances about the rainfall. So then the sequence of events. And again, we've gone through this. I'm not going to dwell on it because we've got a lot to get through tonight. So the sequence of events goes through. You can see train goes through. This is what should have happened. What actually happens is the blue train runs through, collides with the green train. That's the situation. And there's lots of really good detail from the on-train data recorder. Again, context for Bedford. This is the sort of information that you can get access to. So you've got the on-train data recorder here, kind of one of the black boxes on the train that is picking up all the information, including where the brake is being applied, the speed, and the permissible speed as well. So you can see that it's already running too quickly in places, run too quickly through the loop, and then too quickly down the. You can see the sort of challenges with speed here happening, and then it gives a bit of an idea of exactly where that all happened on the place of the map and the speeds of the trains at various locations. So there's the kind of the context. The sequence, as I say, we will push through that. The events following the accident, the driver of train 1 Juliet 25, the one who had kind of been in the train doing the sliding, checked on all of their passengers, made a GSMR railway emergency call to the signaller to report the collision, request the attendance of emergency services. Dyfed police were coming along, and so on and so on. So all the information here. The driver of 1 Sierra 71 was sent to hospital. It was not tested for alcohol and drugs because of their injuries. There's no evidence of the presence of drugs or alcohol in the driver. Yeah, of course, they were just doing their job coming up the hill at a very low speed at that point, presumably having applied the brake. I think we actually, let's just quickly flick back that. So driver. Yes, okay. So they had a conversation with the signaller, and driver 1 Sierra 71 mentioned the train was struggling with low adhesion on the uphill gradient. Okay. So signaller had a conversation, and then the traction power was shut off to stop at the signal. And 9 seconds after speaking to the signal, the driver applied the emergency brake and attempted to leave the cab. So basically, almost certainly in response to seeing the approaching headlights of 1 Juliet 25. There you go. So again, I won't dwell on the events following. The analysis is what we're going to go into. So that's kind of where this comes in, right? So Oh, wait a minute, I'll have broken that. Where's my OBS? Let's go half face again briefly. There we are. So, yeah, causal analysis. So if you want to know more about leaves online, how we tackle them, there's an old episode that goes through that, and there's more to talk about on that one. But let's briefly talk about the way that factors interrelate, because we've talked a bit about the Swiss cheese model, which is that you have threats of some kind, threats up here of some kind, and you have various mitigations, and these mitigations will always have shortcomings, flaws, and so you add more mitigations. And generally, these mitigations, the more mitigations you add, they will always have flaws of some kind, but the more mitigations you have, the less likely it is that something gets through. But something will always get through when you have a high traffic situation. And so it's how those different mitigations interact that, prevent your threats becoming consequences, right? So that's the Swiss cheese model. The RAIB takes a different approach. So they have a slightly different approach. They use what's called fault tree analysis. And the culmination of fault tree analysis is the output of the report is that we have an immediate cause, which is the trigger of the crash. And I've talked about this in the context of the Spanish high-speed crash, when everyone was going, you don't know what's, how can you say this? How can you say that? It's like, well, the trigger of the crash is the easy bit. In the case of Bedford, we know what the trigger of the crash is already. That's the easy bit to understand generally. The immediate cause, the trigger of the crash. The things that require deep investigation are two key elements, really. The first are the causal factors. So those are the conditions that, if eliminated, would have either prevented the crash or limited its consequences. So causal factors. So that's a causal factor. Get rid of that causal factor and you'd have prevented the crash. So in a way, you can see how this relates to the Swiss cheese model. The other is underlying factors. These are conditions that made the causal factors more likely to occur. So you can see how there's a relationship between underlying factors, causal factors, and the immediate cause that resulted in the crash or derailment. Let's go back to the report, which requires me doing multiple face juggling. You know what? You can cope with me just doing having a little bit of visible green screen. No one minds. So let's see. Right. So wheel rail adhesion. We've talked a little bit about there's some context here for wheel rail adhesion, what that looks like. Go to that episode where we talk about the science behind it, but fundamentally we use sanding systems to deal with the situations where there's aggressive lack of adhesion, that's grip between the wheel and the rail. When you have a friction system like the railways, grip is everything. And we run a system that is fundamentally low friction because it's very energy efficient. The consequences of that is that adhesion is on a bit of a knife edge, and that's why autumn is one of the most challenging, arguably most challenging season because of leaf fall. And climate change isn't helping with that because we're getting more storms, which result in more leaves being dropped at higher amounts, which the railhead treatment train and other mitigations that we run to get rid of that leaf mulch, which gets crushed to a pulp, by the way, and results in a very slippy railhead. Those mitigations become harder to kind of administer effectively. So there are sanding systems fitted to those trains. So there's a bit of information about the sanding systems, and and then also discussions about the braking systems on the trains as well. So we're not, and wheel slip protection is a key thing. So you're kind of like anti-lock braking like you have in your car. So this is where we get to the identification of the immediate cause. So train 1 Juliet 25 passed its authorised stopping position and entered a single line occupied by approaching train 1 Sierra 71. That's the trigger. The train slipped into the path of the train coming up the hill. That's not that useful or interesting. We don't really learn anything from that, and that is kind of why why Bedford is worth mentioning loosely, is because the RAIB have published today what we know about it, and really what they've done is identify the immediate cause. That is not hugely useful. It doesn't give us much insight. So at this point, there's not much that we can say, which is why that's the limit of what the discussion is going to be really on Bedford. So causal factors is what resulted in, get rid of one or more of these and the accident doesn't happen. So let's see. The approach of train 1 Juliet 25 to the block marker. So the train was unable to stop at that block marker. So it's a block marker rather than a signal, because it's in cab control rather than conventional signaling. So these are block markers rather than signals. The blue, you might have seen the blue square with the yellow triangle in it. I think it's that way around. And therefore exceeded what's called its movement authority. Basically, it's a SPAD. It's the equivalent of a SPAD, basically. So that was the kind of the first of the causal factors because of the lack of wheel rail adhesion. The next one is the fact that the wheel rail adhesion was unable to support the required braking because sand was not being discharged. So there we go. So then you get the next causal factor. Well, that happened because of this. Then you see the next causal factor. So you see all the information, plenty of data here, by the way, about the low adhesion event, the weather, the varying sort of adhesion factors at play here. So lots of detail going on. You can see there's analysis of the condition of the railhead in the immediate kind of aftermath of the accident, giving an idea of the condition of the railhead. So they can do testing of that fairly quickly. There's not visible contamination like oil or anything on the wheels. So so there's some sample collection going on actually on the day after the accident. So you can see they've actually collected some of that leaf mulch sort of scum to sort of look at what the conditions are. So let's go through all of this analysis, because that is obviously the key point. This is a major causal factor. The first one is like, well, it's quite simple. It went past the block marker. It did that because of a low adhesion event. And so here's all the analysis looking at that low adhesion event. And then the next one is, well, what about the systems that would prevent that low adhesion event? Well, there were the train-borne sanding systems. Well, they didn't mitigate it because the automatic sander was not working and the driver did not use the emergency sander. So the automatic sander didn't work and the emergency sander was not used. So again, it's like, well, okay, that then raises all these questions about, well, what was the condition of the automatic sander? Well, not so good. There are some blocked hoses, that kind of like, that's... the blocked hoses, and then the electrics seem to have had problems and not worked. So there's all the going in through all the various kind of technology, the isolation switch, and all these problems. So you can see that all these issues with the low speed relay. So the ability of an electrically active sander to clear a blocked delivery hose. So all this analysis to go through and pick up, all these details. And then the fact that the emergency sanding system was then not activated, and then some of the consideration of whether that would have stopped the train, and also what you go into then understanding the driver training. So the detail of that. Then the next causal factor, which is the approach speed of the train towards Juliet, we're going to call it now. The approach speed of Juliet towards the eastern entry to Talerddig Loop was such that the subsequently required deceleration could not be sustained with the available wheel rail adhesion. So basically, the driver was going, or rather, the driver had been given. It's not necessarily the driver controlled the train, was that it was really too fast for the conditions at that point. But that doesn't necessarily mean that it's driver error, as we'll see. There are challenges here with the indications being given to the driver by the ETCS system, a system that is inherently saying, drive the way I'm telling you to drive, driver. Now, it's not necessarily that that's bad, but if you haven't got enough parameters, for example, to do with low adhesion, as is about to be demonstrated in this section, then that is potentially leading the driver to drive in a way that is not appropriate for the conditions. And yes, it is ultimately the case that the driver has to drive for the conditions, but if you're in a system that is telling you the way you're supposed to drive, then, behaviorally, ergonomically, the consequences are going to be different. So, you can see, so this is a lot of detail that goes into the speedometer, the sort of on-screen interface, if you like, the kind of the driver-machine interface, I believe it's called, that kind of gives information about what's the speed the driver should be doing. And there's a lot of information there. There's a lot of detail here about the fact that you get pre-indications with kind of slight differences in color. You've got all sorts of different color changes. You've got color changes of yellow and then red, saying that there's an overspeed. As we'll go through, though, these aren't that clear, and the driver's understanding of these has been demonstrated as being not great. There's a good graphic here showing the different profiles of trains. The red is Juliet here, and you can see the difference. What stopping trains should have been doing and what continuing trains do. But this paragraph is key. The concept of a speed restriction warning masking notifications for the next one was identified during the early testing phases of the Cambrian ERTMS scheme, when the previous train operator was responsible for operating trains on the Cambrian lines. The Office of Rail and Road, the ORR, you're all familiar with the ORR, Google it if you're not, raised concerns relating to this potentially causing drivers to mishandle trains and advised the project to avoid closely spaced cascading speed restrictions, a bit like these. RAIB has not been able to establish what action was taken, as there is no record of a formal response to this concern. See paragraph 411. So you can see the challenges here. The next one is, having passed the block marker, Juliet entered the unoccupied single line. This is kind of saying, well, no physical infrastructure was there to stop that happening. So no engineer mitigations. There's a bit more about that later on. And then the next one is beyond the block marker, that the wheel rail adhesion was exceptionally low. So at this point, the train had it was a downhill, and there was no chance of the train managing to get adhesion with the railhead at this point. And then you can see lots more kind of analysis of that point. No engineered mitigations existed to prevent the train entering that occupied single line. Talking about traps, for example. This is an interesting one here. So signalling sketches provided by the Signalling Record Society show how the track layout at Talerddig has had many changes since the late 1800s. There were trap points that were provided in 1968. They were removed again in 1986 when the track layout was prepared for the re-signalling under RAIB. And there were no changes then made when the ERTMS system was commissioned, although the points were converted to power operation in place of the train-operated points used under RAIB. Because the use of trap points involves intentionally derailing rail vehicles, their use is limited to very specific circumstances. Now, I've already said this, so for the sake of time, I won't dwell on it, but that's why they were not installed. Understandably, were not installed here. Does that mean that there's a similar or alternative mitigation should have been applied here? That remains to be kind of assessed, really, but that's the reason why there wasn't a set of trap points there. We'll get to that momentarily. So there's a lot of information about the RTMS. The next is then train Sierra was permitted to proceed to the end of its issued movement authority. That's the train going up the hill, the innocent train, if you like. And this is another interesting paragraph, right? So ERTMS does not incorporate a function to automatically send a stop command to trains with movement authorities already issued where the overrun is not in direct conflict with their route. Even though train 1 and Juliet 25 had entered the single line and was now foul of the single line, it had not passed it had not passed the previous block marker. So I'm not going to call it a signal. So it was not yet in conflict with the movement authority issued to train Sierra. The provision of a facility to automatically send a stop command to trains with a valid movement authority in the event of an overrun without a direct conflict. So that's basically saying, you're probably going to come into conflict in a minute. You should stop. It would be subject to a client requirement. What that's saying is that's not part of the baseline standard. You have to request that as an additional function, an additional feature with cost and complexity associated with it. This request would have originated from Network Rail, but was not made, so the facility was not provided on the Cambrian lines. There we go. So it's as simple as that. There's a bit of detail about the use of GSMR. That's the kind of universal sort of radio system that we have for contact. So a good bit of detail in here. An impact on collision speed, so a kind of a mitigating factor on that was the fact that there was a kind of a gel applicator located that was not operational that could have reduced the speed of the train had it been functioning. There's a lot of analysis they do to have a look at that. And also the use of adhesion modifiers by the railhead treatment train, which could have also been applied to potentially influence the overrun, if not get rid of it. They say it's very difficult to quantify its influence. And they talk about the fact that it is not used regularly, or in some instances not used because there's a perception by some engineers that it actually attracts and sticks leaves to the railhead, and it doesn't let them blow off in wind, and therefore actually makes things worse. We'll come back to that later. And then there's a bit of kind of performance of the vehicle structures. Well, there was a loss of cab survival space on train Sierra. So the train coming up the hill, you can see the severe damage. The cab is basically compressed into very little space whatsoever. Key thing, you can see how much the desk has been pushed right up against it's a small picture there. I know it's a bit of a postage stamp, but you can get the PDF yourselves. The desk has been pushed right into the where the driver would have been sat there. It's really not good at all. And so there's a couple of paragraphs here on crashworthiness. It's something that I care very much about. Well, much as I love the 158s, these also not great. They had to comply with a sequence of various standards, but the standards they had to comply with gave forces that the cab had to survive, but not given collision scenarios, as modern crashworthiness standards have to. So this is one of the first application of welded aluminium in UK train construction, and so a lot of work went into understanding its performance, and British Rail in 1989 concluded this: the Class 158 is not a good crashworthy structure. High force levels and low energy absorption at low impact velocities are evident, with deceleration levels approximately twice the suggested values. What that's saying is the train's too rigid and there are no energy absorbing features, which means that a lot of force spikes into that cab, resulting in high forces for the driver and also high forces for the components, which can fail, resulting in a loss of cab space. So in 1991, the 158 cab structure was crush tested in a controlled environment. British Rail concluded that the energy absorbed by the cab ends in the test was sufficiently high to meet British Rail's latest standard, but the peak forces generated during the test were much higher than in comparable steel vehicles, and the mode of deformation rather aggressive. Steel is better at crumpling than aluminium. It is, so now that we have other sort of FEM design, we can do a better job of that. See also the 810 and how well it performed in the Bedford crash, but the aluminium extruded in this way for the construction of the 158s turns out doesn't perform that well. So yeah, the cab not great to be in one of those. And yeah, rigor mortis 69 pointing out these blunt-ended trains have little space to play with to add crash structures. Absolutely. And then the performance of interior fittings as well. So saloon tables. And there's always a chat about seat belts, and that's worth just picking out the fact that the RAIB believes that the RSSB's post after Nervit justification for not fitting seat belts is no longer supported by the fact that modern trains are better at not losing cabin space. Greyrig, for example, and Talerddig both, the passenger cabin stayed largely intact because of stronger trains, but that means that the forces were higher and also the logic of seatbelts being that they allow people to move around inside a squishing train doesn't apply if the train isn't squishing, people are just flying around. Does that mean that seatbelts being fitted is actually a good idea? Well, there are lots of reasons for that not to be the case. So, performance of interior doors, access panels that were causing problems for the emergency services, some of the things, and then underlying factors, which are very important as well. Underlying factors such as the fact that there was a long-standing misalignment between the system safety models used for the Camry RTMS signalling system and Class 158 rolling stock. So there's a kind of a fundamental disconnect between those two trains, those two systems, the train and the system controlling the train, which is, not ideal. I think the 3 paragraphs here that really summarise this. Trains on the Cambrian lines are not expected to overrun their movement authority based on the stated maximum allowable rate for an exceedance of the permissible speed or distance. So basically, the system is designed on they will never overrun. This, however, requires constant supervision of trains operating under ETCS to prevent such overruns. So, that means that any train operation is therefore critically dependent on the train's ability to control its speed and stop within the distances adopted by the signalling system design. The train's ability to deliver such control is, in turn, dependent on a sufficient wheel rail adhesion level. And the accident at Talerddig demonstrates that the 158, in the way that it was being maintained, could not provide the sufficient wheel rail adhesion levels. So there is a fundamental mismatch in risk management between the RTMS assumptions and the capability of the 158. Really important systems failure there. Kind of arguably the most fundamental failure, I would say. These 3 paragraphs really represent the major failure in what happened at Talerddig, really. Assurance of automatic sander operation. So TFW's processes intended to ensure the operation of the automatic sanding system were not sufficiently effective. Yep. TFW did not have a full understanding of the RTMS system and its drivers' interactions with it, which is a probable underlying factor. So this is kind of a key paragraph as well here. The nature of in-cab signalling systems such as ETCS means that to fully exploit the advantages of in-cab signalling while avoiding kind of SPADs, basically. Sorry, what is the SBI? Someone in the chat will tell me what an SBI is, but basically I think that's like an intervention of the system, perhaps, or an automatic, maybe it's an emergency brake. Drivers will focus on the DMI, that's the screen, and keep close to the speed indications it provides. This contrasts with conventionally signalled lines where drivers must use their route knowledge and the information provided by signs and signals to plan ahead and control their speed appropriately. This change in emphasis may mean that drivers operating with in-cab signalling systems are less aware of upcoming changes, such as being routed into a loop, where the diverging route has a lower line speed. This is supported by a survey which RAIB undertook of drivers on the Cambrian lines who reported that they felt too little information was provided by the screen, the RTMS screen, about the route their train would take at stations, junctions, and passing loops. Academic research suggests that more information provided in the planning area could assist drivers in developing more effective driving strategies. Absolutely. So had the driver known inherently that they were going into the loop, they may have been approaching at a lower speed to manage the consequences of that. Yes, so... Doug Pally, thank you so much for the £10. Hi, Gareth, and thanks for what you do. The emergency action signs on trains are all based around being mobile. No instructions for people who can't. Are we left to last for FRS, for the fire and rescue services to evacuate? often and uncomfortably the assumption is, the people in the wheelchairs, they'll just kind of wheel themselves into a little safe area and we'll just come and get them later. Yes. Yeah. And I just continue to not think. Service brake intervention. Thank you, Smitty91260. Yeah, service brake interaction. So basically like an automatically applied brake application. Doug, it's a very point, and I think we continue to not do a good enough job there. And again, it's just like get disabled people involved early doors with the design rather than it being an afterthought would solve a lot of those problems. RAIB also found there was confusion over the different warning colours attached to the speed hook, with some drivers unaware of the existence of the orange colour. This indicates a lack of complete knowledge of the system by some drivers. In addition, research suggests there's little to no difference in the connotation of these colours, given that white, yellow, or orange can signify a warning. A lack of discriminability between these similar colours could also potentially create confusion. Research also shows that if the system is not transparent or explicit, drivers may find it difficult to form a complete, accurate, and effective mental model to support them in the driving task. Principles of good display design also include the importance of minimizing perceptual confusion and the need to make the discrimination of modes as visible as possible by employing salient and visual cues. This lack of understanding of the different colors of the speed hook highlights the importance of effective training to ensure drivers fully understand system-generated warnings. However, TfW lacked the detailed knowledge of the operation of the system to be able to provide the necessary information to the required depth to drivers. That's scathing. Basically, drivers not having a full understanding of the system that they were using to drive trains. Really quite brutally scathing. And so then the other issue was the fact that TfW were not training their drivers sufficiently to prepare them to respond appropriately in an emergency situation in the cab. And there's a paragraph here that I want to read. When the RTMS system was initially implemented on the Camry lines, a Class 158 cab simulator was provided by Network Rail to facilitate driver training. This simulator fell into disuse and was subsequently decommissioned. The loss of this simulator removed a potential tool which could maintain driver skills and knowledge when faced with out-of-course and emergency situations such as those encountered by the driver of Train Juliet approaching Talerddig. The simulator may also have been useful to refresh drivers on the masking effect, which may affect warnings on the screen, had this issue been fully understood by TfW. So a serious failure there of the railway. Network Rail did not have a detailed understanding of the effectiveness of wheel rail adhesion modifiers. This is a possible underlying factor. A common theme reported by seasonal delivery staff was a lack of clear guidance on the effectiveness of adhesion modifiers. So things that shoot gel or paste onto the head of the rail to improve how sticky the rail is to the wheel of trains passing over. Although most seasonal delivery staff reported good formal and informal means of getting advice and support, several reported a lack of knowledge about the performance of adhesion modifiers. One person stated that they believed that the decision not to use adhesion modifiers was sometimes based on a feeling within a route or the opinion of influential staff. And now the next one to kind of compound onto this was that Network Rail's seasonal delivery team for the Wales and Borders route was operating with reduced resources and the seasonal delivery manager role had no formal competency framework. Although the absence of staff resources had meant there was reduced capacity to explore new developments, the overall approach to seasonal management was compliant with Network Rail standards. This is such a classic Network Rail line. So there were lack of staff to actually think about the future and maybe prepare and do research, but they were enough to just keep on top of the role as required by the bare minimum as required by standards, is what that first sentence says. It's painful. RAIB found no evidence that these resourcing issues created the conditions for the Talerddig accident to occur, or of any concerns being identified by other rail industry parties working within the Wales Borders route regarding Network Rail's preparedness for the 2024 autumn leaf fall season. So resourcing not regarded as being a factor. But I think it's worth saying that, but had we been using better technologies or had a better understanding of the technologies, we could have been better at preventing the low adhesion event in the first place. Some members of TfW staff had received no training on the emergency equipment provided on their trains. So there was a driver, a guard, and a host. And the guard and host were not regarded as safety critical staff. The host of the train was not regarded as safety critical staff and had not received any form of training to cover actions which could be required in the event of an emergency. This is why all the staff on the train have to be safety critical, because they can all act if there is an emergency. So yeah, rightly the unions will be picking up on that one, I suggest. That's a very interesting line, that one. Yes. Other defects in the sanding systems. Low sand delivery rates can reduce the potential benefits provided by train-borne sanding systems. So there's a bit of information about sanding rates here. Now, the last one is that the RR gets its own little section here, the actions of the Safety Authority, for which I'm going to refer to just one paragraph here, which is, I think, a little bit instructive about the conditions of the ORR. Although RR supplied RAIB with a significant quantity of documentation about its certification of the Cambrian Lines ERTMS project, most of the relevant documents from the period from 2012 to 2022 were missing. ORR explained that this was due to an issue with the computer-based storage system in 2017, which had resulted in the loss of many documents. From the remaining documents, it was not apparent how any concerns about the specific issues raised were resolved. The previous few pages talk about issues raised in the deployment of ERTMS here. Additionally, no references were found to any considerations of the reliability or performance of the automatic sanding systems fitted to ERTMS-equipped Class 158 units. Yes. So, let us jump then to sort of summarising those conclusions again for the benefit of those who are perhaps jumping in. So the immediate factor was the fact that the train passed its authorised stopping position, entered the single line occupied section occupied by the train Sierra and walloped into it. The causal factors were that the train was unable to stop at the block marker where it was supposed to, because the wheel rail adhesion was unable to support the required braking. The sanding on the train didn't help. It either didn't function or wasn't operated, and the approach speed was too high for the conditions. And then, having passed the block marker, it went into the single line section. The wheel rail adhesion was even worse, so there's no chance of reducing its speed, and there were no engineer mitigations to prevent the train entering that single line section. So those are the causal factors. Those kind of A and B with some splits leading into it. So you start to see the kind of that tree, the factor tree there leading to the failure. And then we've gone through, the factors affecting the severity of consequences are that train Sierra there was no system to stop train Sierra earlier. There was a traction gel applicator that was not operational. The use of an adhesion modifier delivered by the railhead treatment train wasn't happening. It was not operating. There was a loss of cab survival space because of lack of crashworthiness in the 158s. Interior fittings in the train were not ideal, and indeed the external access panels caused problems, or internal access panels caused problems as well. And we've gone through those underlying factors and observations as well. So that goes into kind of the detail. Really on that front, there's a lot of detail there, but it's absolutely all worth going through. Now, after a brief pause, we'll come back and look at the recommendations. As ever, if you want to arm yourself with the tools to make transport better, then joining the Patreon for £5 a month is a great place to start, giving you the free audiobook of How the Rails Will Fix the Future, as well as access to the weekly bonus episode with the full back catalogue, adding a big chunk to the Rail Natter canon. Go to patreon.com/Gareth Dennis. And the bonus tonight is that we will deep dive Q&A this. We'll do a bit of a Q&A. So for those of you who are in here, are already Patreon supporters or want to be Patreon supporters, want to have a deeper chat about this, get stuck in, come join. And we will, tonight's episode, bonus episode, we will be going into a deep dive. That'll be at 9:30. Of course, there's something else that you get if you're a Patreon subscriber. That is Transatlantic, the podcast, with myself and Justin Rosniak. We are about to be recording episodes 3 through 5, I believe, which will then be going up at the moment monthly. But if you love it and lots of people subscribe, if there's a huge spike in Patreon subscriptions, then let's be honest, we're going to be increasing the frequency of Transatlantic. So if you want to watch more of that, get subscribing. This week sees extreme heat across England, particularly in the south, where temperatures may well exceed 40 degrees Celsius. The last time this happened was in 2022, and for the railway, and indeed the built environment at large, we saw severe impacts as a result of this. There is a fantastic document that's worth downloading to understand what the impacts are on the railway, because the Climate Change Act requires Network Rail and other public and private bodies to understand climate change, not just in terms of emissions reduction, but the response to climate change, what's called climate resilience, actually having infrastructure that can survive those changing conditions, of which temperature is a key one. It's a fantastic document. You can just download it by going to the just googling Network Rail Climate Adaptation Report. The 4th edition is a PDF out there available, well worth downloading. Within it are several graphics, really useful graphs that explain, that allow us to understand the impacts from different forms of climate. In the case of heat, well, this graph is very useful. It shows Schedule 8, which is the kind of the daft wooden dollars way that the infrastructure part of the railway gives money to the train operating part of the railway if there's some infrastructure problem that delays trains. So Schedule 8, in a way, is a measurement of delay minutes. It's about its only useful application is in collecting those statistics. What this graph shows is overall climate impacts since 2006 up to 2024, and you can see that that number overall is absolutely increasing from about £50 million a year up to £150 million. Particularly for this discussion, what's really interesting here is you can see heat, the actual impacts from heat increasing over time there, shown, the breakdown of different climate impacts, shown there, heat in red, and you can see that that is also increasing quite dramatically over time with that big lump in 2022. Another graphic that's quite useful is breaking down those impacts, those climate impacts, by discipline, by technical discipline. So you can see that the orange there is heat. The biggest by far, you see that big orange blob, is for health and safety and welfare, so staff safety. We'll get to that in a minute. But at the top there, you can see track is also very heavily impacted by heat. Indeed, the Climate Change Adaptation Report goes through lots of different ways in which heat specifically impacts on the railway, alongside lots of other things. Water is another key threat from climate change to the railway. So track buckles constantly get talked about. If you're hearing a news report about the heat, then yes, people are going to be talking about track buckles. How do we manage track buckles? How do we manage those thermal forces? Well, of course, the issue here is that steel, the rails are made of steel, and steel expands in the heat. And so that expansion has to go somewhere. Now, there are different ways that we used to manage this. We still indeed have fish-plated joints, joints that are essentially two separate 60-foot lengths, 18 to 8 meter length rails connected by joints that have a fish plate either side, bolts through them, and an expansion gap that closes or opens depending on how hot it is. In winter, those joints are open, and in summer, they might well be closed up. The problem with those joints is that under traffic, they have a nasty habit of disintegrating and derailing trains, which is why we moved very much away from them in the middle of the last century. And they're also extremely challenging to maintain. There are hundreds of joints in any given stretch of a mile of mainline. You may have 100 joints to maintain. That's a serious labour burden at a time when we have fewer and fewer people actually out maintaining our tracks. So the other way that we can manage, connect up rails to manage those forces is through welded joints. Now, when we weld two bits of rail together, we don't just do it at any given temperature. No, we actually make sure we cut a specific gap in the rail, or we leave a specific gap in the rail, and we actually pull those rails together before welding them to make sure there is a certain tensile strength in the rail. Because if you have a length of rails are essentially long and thin. In tension, so if I'm pulling them apart, they maintain their shape very nicely. As soon as there is a compressive force, they buckle, right? That's the issue with buckling track. What we do with the rails, with welded rails, is that we actually apply a tensile force to keep those rails to shape so that they can cope with higher and higher temperatures. Now, in the UK, we have a temperature at which you move from tensile to compressive stress. It's called the stress-free temperature of 27 degrees. For legacy installations, actually new installations are using higher temperatures now, and we're probably going to move into a situation where we might well consider case-by-case basis of what that stress-free temperature needs to be. More on that perhaps in another rail natter. In the meantime, we pull those rails together, weld them up, and so those forces, those longitudinal forces, are distributed through the track. So we have stronger track materials, heavier track materials, concrete sleepers, and also crucially the stone that supports the track, the ballast. We have what are called shoulders here, either side of the track, that actually help to maintain its lateral stability to avoid buckles happening in the first place. Of course, if you can limit the amount of the temperature, the sun getting into those rails, you can also keep those rail temperatures down. A kind of a rule of thumb is that if you have a given air temperature, then the rail temperature might well reach 20 degrees hotter than that. So for 40-degree air temperature, you might have 60-degree rails. Painting the rails white is one way to manage that, particularly in weak areas where you've got switches and crossings, junction areas, you might well paint the rails white, over bridges perhaps as well. Italy does this pretty much for their whole network. We are a bit more selective. In more extreme ways, you can use different track forms. So slab track, for example, being used for the majority of HS2, used for lots of bits of kind of suburban rail around the world, is much more resilient to high temperatures. It's much better at keeping the rails in place in those higher temperatures. But it's much more expensive, of course, to install, even if it is then essentially maintenance-free from that point. and perhaps not suitable for all conditions. The issue, of course, is, well, not of course, the issue is that plain line tracks, so just two rails going off in both directions, is less of an issue, to be honest, from buckling, as those busy, complicated areas like this, like Clapham Junction, like Victoria down in London, those areas of complex S&C, or busy S&C, switches and crossings everywhere, that are what we call unstressed S&C. It cannot cope with those compressive forces. It's too weak. It will fall to bits, buckle, disintegrate under traffic. This is bad. Requires speed restrictions or closures. What's the way to fix this? Well, track renewals. Replacing those track materials with new, modern S&C that can be stressed allows you. So this is Thameslink renewals near London Bridge about a decade ago now. This whole area can now run at 59 degrees Celsius. So you can run trains through here at full speed, basically with a 39-degree air temperature. So it gives you an idea of the fact that we can run a railway if we renew the track. So track renewals are climate resilience, are climate action. What about other parts of the railway? Overhead electrification. It is absolutely, a railway is incomplete without overhead electrification, frankly, but it is also vulnerable to heating. Again, we have overhead cables, overhead wires, overhead lines. As they get hotter, they're metal, they will expand. And how does that expansion get? Well, it results in sagging. You have sagging. Now, we deal with that by having tensioning systems that actually tension for the sag. So as the cables expand, there's overhead lines expand, then the tensioning systems account for that up to a point. And indeed, fairly new systems installed in the UK, overhead electrification systems, were designed to cope with 38-degree air temperatures. You'll be glad to know that standard has been updated. But of course, we have lots of legacy electrification that is either doesn't have auto tensioning at all or isn't designed to cope with the temperatures that we get nowadays. So that can also be a challenge requiring speed restrictions, because if you have a sagging cable, that can get snarled up in the pantograph and result in dewirement and a closed railway. What about people on trains, though? Because the staff and passengers on trains, not all trains have air conditioning that can cope with high temperatures, even 35 degrees, let alone 40 degrees. So that is a major challenge. But what about our signalling systems? Because as we have centralised the operation of our railway into larger and larger rail operating centres, nerve centres of large regions of the railway, you can see the kind of the workstations there. If you've got a whole team in one of these fantastically modern workstation, kind of working environments, and the HVAC fails or the aircon is not up to snuff, they can't work in those conditions. They go home, the railway shuts. That's the end of that. Potentially worse, if you have the room with all the solid state interlocking in it, all the basically solid state hard drives with all the signaling system in it, and they all melt because the air conditioning has failed, your railway is out of action for days, weeks, months, maybe. So centralization is in many ways good, but it creates these new challenges. So for trains and for our rail operating centres and those centralised nerve centres of the railway, air conditioning becomes a absolutely safety critical part of that design and needs to be taken very good care of. Of course, in these extreme temperatures, as we saw in 2022, bits of the railway can just melt or burst into flames. And there is, less and less you can do about that in extreme heat. And extreme heat is what we're going to be seeing more and more and more of. There's more for us to do. And of course, the big challenge is, do you divert funds away from expansion and capacity increases of the railway, so therefore reducing carbon emissions by driving modal shift, just for the sake of climate resilience? Or do we need to invest more in our public transport systems to get people off the roads, which themselves have got their own issues of buckling, melting, and so on? So, the recommendations at Talerddig. We're going to get into these. We're going to go straight back to the report. In fact, no, before we do that, we're going to bring up the video, the RAIB video. And I'm not going to just narrate what's being said, but you can read it if you like, because we're going to go through the 9 recommendations in sequence shortly. But suffice to say, there are a number of recommendations kind of in advance of these 9 that basically are reiterations of things that the RAIB have said, please do this already based on other accidents. Carmen, for example, and others as well. So there are a few. It's worth reading through those recommendations because they are as valid as the recommendations that are new emerging recommendations from specifically from Talerddig itself. There's some photos of you've seen a few of these photos from the video earlier. But this gives an idea of this is the narration here is kind of essentially listing off the 9 recommendations, which we will go through shortly. They cover training, they cover Well, we'll get there. We'll get there momentarily. I think the one thing that I wanted to kind of reminding railway staff of the importance of reaching a clear understanding when conducting safety critical communications is sort of the last recommendation, which is really a key one. So, what of those recommendations? I'm going to go through them here, and you know what? Let's go through them in the document first. Let's get the old PDF face going here. There we go. I'm here. So, what are those? So that's all the previous recommendations and actions. So these are the recommendations here. So piece by piece. So you've got them on screen. You can read the detail. So the first is that the RSSB, working in conjunction with the owners and operators of rolling stock fitted with sanding equipment, should review and update the standards and guidance relevant to the design, maintenance, and testing of that sanding equipment. So, okay. Obviously, there's lots of extra detail. Number 2, Angel trains should improve the availability of sanding systems. That means how good and effective the sanding systems are fitted to the 158s. Okay. Network Rail, working in conjunction with TfW, should review the assumptions which form the basis for the decision to undertake only simple overrun risk assessments on the Cambrian lines. It's saying, do this review, and should the original assumptions be found to be invalid, I would suggest that this incident potentially would err us towards that direction. Consideration should be given to undertaking that full detailed overrun risk assessments in accordance with RIS 386 CS. Recommendation 4 is considering the opportunity to protect trains approaching the location of potential exceedance of movement authority at the earliest opportunity as part of its client requirements. Basically, that's saying Network Rail should, as quickly as possible, update the RTMS and ETCS standards or requirements and add that as a functionality to the RTMS, which, to be fair, is a thing they can do. They have the capability to do that. That's one advantage of the signalling system. Not having to go and build a bunch of engineering to physical stuff on track. In theory, you can just add that as an additional functionality to the control system. Number 5 is ensuring that TfW have a better understanding of the relationship between the drivers and ERTMS. In terms of, including things like training and the competency and so on. Might apply to others, not just TfW as well, operating trains in areas with ETCS. The next one is better TfW. TfW need to do better training for their drivers in emergency conditions. Recommendation 7 is about Network Rail understanding, getting a better understanding via research and testing of low adhesion mitigation. Recommendation 8 here is, you can see all the detail going into the fact that this is looking at once again, RAIB having to go look at the quality of your train fittings for a safety perspective. And then recommendation 9 is about on-train staff working for TfW and making sure that all staff on a risk-assessed basis should have adequate emergency competencies. So that's those are recommendations, and then there's a learning point which we touched on in the video momentarily ago. There's the appendices, and some nice extra detail there, lovely extra detail going through, and that is the report. So let's just very briefly go through those recommendations, shall we? So, a reminder, recommendation 1 is to review standards for on-train sanding kit. Recommendation 2 is to eliminate failure modes for 158 auto sanders. Recommendation 3 is to reassess the need for full overrun risk assessments in the ERTMS areas. Number 4 is to improve ERTMS to better protect other trains. Recommendation 5 is to improve ERTMS policies, training and assurance. Recommendation 6 is to improve driver training for emergencies. 7 is more research on low adhesion mitigation. 8 is to review the standards for train interior fittings, and 9 is to review the training requirements for all on-train staff. Now, what happens to these recommendations? They get sent out by the RAIB to industry, and industry, through various bodies, or our Network Rail, the train operators, sometimes the unions, will respond to those. Now, the Carmen derailment happened in 2020, and 4 years later, this is what the RIB had to say about the progress on the recommendations of the current report. A lot of work has been undertaken and progress made in closing the recommendations in the intervening years. However, 8 recommendations remain open, indicating that there is still work to do. 4 years after the disaster, that's a reasonably scathing thing for a very gentle and tepid body like the RIB to state. And then we have Bedford. The RAIB published its initial findings earlier today, and I hope tonight's episode has been valuable in helping you understand how those investigations look, how they identify the cause, and the different interactions and their outcomes in a two-train collision. There's little we know beyond the trigger, but the main thing I want you to take away tonight is this, right? I'm just going to go big face for this because it's really important. There is never a single cause, never a single individual at fault. Train crashes happen because of confusion, confidence, and complacency at a systematic level, and we only fix that by always challenging that system to do better. Good night, everyone.